Welcome back to this edition of Dr. Bale's Radio. On today's episode, we're talking about emerging infectious diseases, specifically zoonotic spillover and pandemics. Globally, especially in the United States, the overall trend in mortality rates due to infectious diseases has been decreasing, especially when you compare mortality rates to non infectious diseases like cancer, heart disease, and other so called chronic or non communicable diseases. If you look at the trend since the 1900s, there's one notable exception. Right around 1918, there's a dramatic spike in infectious disease mortality that's associated with the 1918 Spanish influenza pandemic, which was a devastating pandemic that swept across the globe and caused significant morbidity and mortality worldwide. Where we are now is still overall a relatively low mortality rate in the United States compared to non infectious diseases like heart disease. And because of these statistics, in the 1960s, the Surgeon General at the time, William Stewart, famously or infamously gave this quote: "The time has come to close the book on infectious diseases. We have basically wiped out infection in the United States." An audacious claim, but based on statistics and graphs like this. So, this is infectious disease mortality rates broken down by different types of disease: whooping cough, measles, diphtheria. And a lot of this dramatic decrease up into the 1950s and 60s was due to the development of very effective vaccines. So the Surgeon General at the time was, I think within his um, right to feel optimistic, because this graph is quite optimistic if you're a public health practitioner. That is until the 1980s, when a cluster of healthy, otherwise healthy young adults started presenting with rather strange disease symptoms. Usually, these kinds of diseases, specific types of pneumonia, for example, are diseases associated with people with really, really weak immune systems. Uh, this signaled the start of the HIV/AIDS epidemic in the United States. And this was really a game changer for emerging or infectious diseases, and it really made us step back and think: do we really have a handle on infectious diseases like we think we do? Since then, we've seen headlines like this: Ebola, Zika, SARS, pertussis, and measles. And of course, the pandemic we're currently living in, the COVID-19 pandemic. And let's not forget about swine flu. All of these new diseases have a name. They fall into the category of emerging infectious diseases. Emerging infectious diseases are those diseases in humans that are new, previously unknown disease outbreaks. They are either rapidly increasing in incidence or in geographic range over the last several decades. Notable examples include, of course, the COVID-19 pandemic, HIV, SARS, Lyme disease, Zika virus, and West Nile virus. These are all diseases, infectious diseases in humans that basically weren't there that long ago. They're new and they're growing. Another kind of classification or category in this realm are the so-called re-emerging infectious diseases. These are diseases that have reappeared after a period of significant decline. So they once were a problem, and then we got them under control, and now they're making a comeback. So examples include measles, pertussis, and gonorrhea. Some of these are due to the misuse or overuse of antibiotics. Some are due to anti vaccination beliefs. And globally, these diseases tend to be clustered in certain geographic locations. In the United States, there are some notable clusters: Southeast Asia, Europe, and Sub Saharan Africa. This is an analysis done by Kate Jones and colleagues looking at global trends in emerging infectious diseases. And they found that there are these so called hotspots of where these diseases are coming from. And this emergence or reemergence of these diseases have complex causes, typically an interaction between social and environmental factors. And we're going to go through a couple of these right now. So, a fundamental question that we need to remember in assessing what the causes of emerging diseases are is this question: can changes to the environment make us sick? Because it turns out that a primary cause for a lot of these emerging infectious diseases is environmental change. Changes to the environment due in large part to human activities, climate change, deforestation, etc. And when we're talking about emerging infectious diseases, we're talking about those diseases that tend to be mediated by ecosystems. This lies in a subfield called disease ecology. So, looking at diseases and the ecology of their origins. So, let's talk about a few causes. Some of these are social and some of these are environmental. International transportation is a particularly important cause, especially when we're talking about pandemics. The world now is a highly connected place. Country boundaries have essentially dissolved when it comes to the transportation of people, products, and pathogens. This so called pathogenic planet or the anthropogenic planet is a big reason why these diseases are able to spread so quickly. In fact, it's now possible to get from a tropical rainforest in sub Saharan Africa to a neighborhood in the Midwestern United States within the incubation period of many of these emerging infectious diseases. So, again, incubation period meaning the time between when you're exposed, when the pathogen enters your body, to when you start developing symptoms. So, you can be exposed to a virus, let's say in Uganda, and be back in your home in St. Louis, Missouri, and still feel healthy within the incubation period. You can see how highly connected the world is by average flight paths. So this is Flight Tracker. This is an average day. Any given day, you'll see airplanes flying around the world like this. The world is highly connected. So anything that happens in, let's say, sub-Saharan Africa or the Amazon or Southeast Asia, it's not a over there problem. It's an everywhere problem. Global is local and local is global. Population growth is another key contributor to why these diseases are emerging. There has been a rapid exponential increase in the population size of the planet. The world population has continued to grow, particularly since the 16 and 1700s, in this very rapid fashion. And it's projected by the year 2050, the number of humans on the earth will reach 9 billion people. So, why is this date important? No cheating. Wednesday, May 23rd, 2007. Kind of oddly specific, wouldn't you say? But why is this an important date? This date marks the first time in human history that most people on the planet live in urban centers rather than rural. Not only is the size of the planet getting bigger, but people are moving together. They're concentrating in urban centers, in cities. May 23rd, 2007, the day the Earth switched from urban to rural. Snapple fact. And with this trend comes the growth of so-called megacities. These are, as the name implies, cities jam-packed with people, high population densities. So you see a lot of these megacities, the growth is in China, but it's in other places too. Southeast Asia, Africa, the United States has megacities as well. And this trend is expected to continue into the future. The rise of so-called megacities. An important consideration when thinking about why emerging infectious diseases are happening. And in many population centers or urban centers, there is a lack of adequate sanitary infrastructure, particularly in some countries where megacity growth is outpacing economic development. So, crowding and marginal sanitary conditions have been linked to increases in infectious diseases. And when we're talking about an infectious disease, meaning a disease that is capable of spreading from person to person, and when we have conditions in which people are living in close proximity to each other, it's not a stretch to think, well, this is a perfect recipe for spreading of disease. Many of these large cities have substantial populations living in informal settlements, so-called slums. These informal settlements often lie within city boundaries, and you can see often the stark contrast between informal settlements and even wealthy areas. But we know that pathogens don't respect socioeconomic boundaries or even little fences like this. So this is an issue for everyone in these cities. But you can see how sanitation and conditions might be right for an infectious disease outbreak to occur. This is the largest informal settlement in Africa, just outside of Nairobi, Kenya. And you can see a lot of the conditions are right for not only infectious diseases, but overall just stress on health. So when people are malnourished or exposed to pollution, they tend to be more susceptible to infectious diseases anyway. Construction of dams. There has been a rapid increase in the number of dams being built across the US, Asia, Africa, and other parts of the planet. Dam construction has been increasing because dams are an important way that we can generate electricity. It's also an important way for how we can redirect water for irrigation. So you can see in Africa alone, the large and spread out distribution of dam construction in the continent. You notice that there are not that many dams being built up here because this is basically a large desert. It's the Saharan Desert. So, this kind of environmental change, remember we're asking the question, can changes to the environment make us sick? It turns out that this kind of environmental change is a key driver of emerging and re-emerging infectious diseases. So obviously, dams affect the distribution of water. Where there was once a river, now there is a lake or a standing pool of water. Turns out that mosquitoes are particularly fond of water. It's how they lay their eggs, it's how they reproduce. You can't have mosquito-borne diseases without water. If you look at the distribution of dams in Africa and you compare it to the distribution of areas with endemic malaria risk, you can see that the overlap is troubling. Dam construction is occurring in places where malaria is occurring. In addition, this increases the risk of diseases like schistosomiasis, which is a mouthful, isn't it? Schistosomiasis. Well, here's what this little guy looks like. And why do dams cause a problem here? So, schistosomiasis is a pathogen that is found in water. It's a waterborne disease, and it basically has a rather complex life cycle in which it releases eggs into water. Uh, for the life cycle to be complete, these little eggs need to actually be taken in by these little snails. And as part of this life cycle, the snails allow this pathogen's next stages of its life cycle to uh, continue. When someone is exposed to water with these pathogen infected snails, they consume the eggs, they consume the schistosomiasis parasite, and the life cycle continues, causing disease in the human host. It turns out that dams actually increase the risk of schistosomiasis for kind of a surprising way. It turns out that there are these river prawns, think about big shrimp basically, and they love to eat these snails. But they also like to travel up and down the river. That's how they complete their life cycle. And when you have a dam, you have blocked the snail's path of migration. And when you have less prawns, there is less predator to eat the snails. So you have this situation where now all of a sudden you have these snails growing and reproducing, and we don't have any more prawns to eat them. So now we have this situation in which people are now exposed to this water and are at higher risk for consuming these pathogen infected snails. So some clever global health researchers have thought, well, how do we get around this problem? And they thought, well, if the prawns like to eat the little snails and the dams are kind of messing up the migration route of the prawns, let's encourage the local communities to reintroduce these prawns into the waterways. And how do you get people to buy into this? Well, convince them, hey, not only can you reduce the risk of schistosomiasis, but it turns out these river prawns are actually pretty tasty. So they've actually gone around into the local communities and taught people how to cook these prawns and care for the prawns and cultivate them. Make sure that their waterways are full of these prawns so they have a good source of food and they have this natural predator for these little snails that cause schistosomiasis risk. This is a good example of so-called disease ecology because we're looking at ecological factors and we're also looking at disease ecology. Climate change is a big one. Climate change, anthropogenic climate change, changing climate caused by human activities, is a significant driver of emerging and re-emerging infectious diseases. There has been a marked, pretty dramatic increase in the overall average surface temperature of the Earth, particularly over the last 50 years. And a lot of the recent emerging infectious disease epidemics are thought to be associated with this changing climate. Why is this? Well, parts of the world that maybe were once too cold for mosquitoes tend to be pretty picky with where they like to live and breed. They don't like it too cold. There's a reason why you don't see malaria in northern Canada or Alaska. And if you have a region where maybe it was just a little too cold for the mosquito, if you have a changing climate or where temperatures are increasing, now all of a sudden you have a lot more areas that are warm enough for the mosquito to live and breed. This increases areas in red here, the distribution of potential mosquito-borne disease locations. So essentially, we have more area for mosquitoes to live. And when you have more mosquitoes, you have more risk of disease in humans. Without mosquitoes, you don't have mosquito-borne diseases like malaria, Zika, and dengue. That's a fundamental risk factor in these diseases. You need to have mosquitoes. And if the weather is getting, or the climate is changing such that more mosquitoes are able to live in more places, you're exposing more people to these vector-borne diseases as a result. In the United States, a vector-borne disease, a mosquito-borne disease that we have, that we're fighting with right now. This is an emerging disease in the United States, West Nile virus. West Nile virus is spread by mosquitoes, and this is some research done recently projecting the impact of climate change on West Nile virus. Areas in red are where, because of climate change, the risk of West Nile virus is expected to increase. And that's because these areas, for example, the northern United States, Northern California, and the Pacific Northwest, maybe they were too cold, or didn't rain enough, or the environment just wasn't right. With a warming and changing planet, now these areas that were not suitable for mosquitoes, now all of a sudden mosquitoes can live there. And when you have mosquitoes, you have diseases that are transmitted by mosquitoes like West Nile virus. Warmer temperatures also may increase the metabolism of mosquitoes, meaning, well, higher metabolism makes them hungrier. And when they get hungrier, they need to eat more. So they bite more. Mosquitoes need blood to complete their life cycle. And if they are metabolizing their blood meal faster, just like with us when we have a higher metabolism, we have to eat more. And when they get hungry, they bite more. The more times a mosquito bites you, the more risk, or the higher your risk of a mosquito-borne disease. Some infectious diseases are purely intentionally released in so-called bioterrorism events. Bioterrorism is defined as the intentional use of biologic agents as weapons. usually for some political reason. And bioterrorism has been happening for as long as we can kind of go back in the records. A famous example was in the 1300s, the Siege of Kaffa. During this time, the bubonic plague or the Black Plague was sweeping through Europe, and there was a famous battle in which this castle was walled off from an invading group of fighters, and they couldn't get through the castle walls, but they still wanted to cause harm to the people within the castle. So they started actually throwing plague infected bodies over the city walls to spread the pathogen within the castle walls. This is an example of the use of an infectious agent intentionally. This is an early example of bioterrorism. More recently, bioterrorism events have been linked to cults. This is a famous example of a bioterrorism event that happened in Oregon, and it was associated with an outbreak of salmonella. This group intentionally contaminated salad bars across multiple restaurants, and they were associated with this cult, and the goal of which was to basically influence local elections by hopefully making everyone sick. And if everyone was too sick to go vote, they could sway the results of the election. Another famous example in the United States was the 2001 anthrax attack. Shortly after the September 11th terrorist attacks, anonymous letters laced with anthrax spores began arriving through the mail at various media offices and congressional offices. People died, and several dozen people got sick. If you look at anthrax in the United States, anthrax is quite rare. You see that we really don't expect there to be too much. And right around 2001, we see this dramatic spike in cases. This suggests an intentional release because you don't typically see these kind of natural peaks. But this does suggest an outbreak. So instead of blaming this anthrax spike on natural causes, they were able to trace this peak or this outbreak to these letters that were being sent that contained anthrax spores. So that was kind of a lot. Let's take a little break, go refresh your coffees, go pet your cat, and I'll see you soon.
Delicious things to eat. The popcorn can't be beat. The sparkling drinks are just dandy. The chocolate bars and the candy. So let's all go to the lobby to get ourselves a treat. Let's all go to the lobby to get ourselves a treat.
Okay, welcome back. I hope you guys had a nice break and are feeling refreshed and ready to learn about the star of the show today, Zoonotic Spillover. Zoonotic spillover is a term that you've probably been hearing about lately in the media. Zoonotic spillover is thought to be the cause of the coronavirus, COVID-19 pandemic that we're all experiencing right now. Zoonotic spillover is the result of human-animal contact in which a pathogen, an infectious agent, is transmitted from a vertebrate animal host to a human host. Many emerging infectious diseases have an animal origin. In fact, it is estimated that about 3 out of every 4 emerging infectious disease comes from an animal. This is due in part to the expansion of human populations into areas where increased contact with humans and animals occurs. Basically, we're building our communities, we're building our houses, we're traveling more into wilderness areas that put us into contact with wild animals. This is a map of sub-Saharan Africa. This is West Africa. And this is a satellite image. Areas in green are forest, and areas in red are which the forest is being degraded because of human settlements. So you can see if there are animals, primates, for example, living in the forest, humans are now living closer and closer contact with these potential disease reservoirs. And it's thought that it is this kind of environmental change that has caused diseases like Ebola, monkeypox, and HIV to, quote, spill over into human populations. In fact, the 3 most devastating pandemics in human history, the Black Death, the 1918 Spanish influenza pandemic, and HIV/AIDS, each of these were caused by a zoonotic spillover event in which the pathogen made the jump from animals to people. Many emerging infectious diseases have an animal reservoir. HIV came from primates. Influenza comes from several animals, migrating birds, pigs, and even chickens. Ebola comes from primates. Hantavirus comes from deer mice. Mad cow disease from cattle. And SARS, the other famous coronavirus, comes from civet cats. And these zoonotic pathogens are dangerous for a couple of reasons. When a pathogen spills over or jumps from animals to people, this pathogen that was once living in animals can mutate and adapt to human hosts and acquire the ability to transmit from person to person. This is when we get pandemics. These zoonotic pathogens can also spill over from animal reservoirs, basically kind of over and over, where maybe it doesn't spread from person to person, but it just keeps happening. The spillover event just keeps happening over and over. And this just causes more burden of disease in humans. So a good example of this is rabies from dogs. We can classify these spillover events, these emerging zoonotic infections, according to several epidemiological stages. The first is where we have pathogens that just hang out in animal populations. They haven't made the jump yet. They haven't mutated. They're just sticking with the animal groups, and they don't leave the reservoir animal population. They are just, at this stage, diseases of wildlife. Sometimes that pathogen, that nasty virus, jumps from an animal to a person. But if it doesn't mutate such that it can spread from an infected person to another person, the virus or the pathogen just stops there. So in this case, the person that gets infected is called a dead end host. because the virus just goes there and stops. This is technically a spillover event, though, because the pathogen has gone from an animal to a person. The third category is when this pathogen not only jumps from an animal to a person, but now is able to spread from people to other people. But this spread is not very aggressive. Maybe the pathogen hasn't evolved to be particularly contagious. And so there's these little kind of mini outbreaks. Sometimes this is referred to as stuttering transmission. And then the fourth category, and the one that we are most concerned with because this is how pandemics start. This pathogen makes the jump from animals to people, acquires the ability to spread from person to person, and it can go from person to person easily. And it effectively transmits from person to person. If the pathogen acquires this ability to go from person to person easily, that's how you get pandemics. So here you can see these different stages in this figure from the reading. So you have up top these animal populations that are the reservoirs of these diseases: bats, cows, primates. Look, a duck. Then we have these spillover events. Sometimes the pathogen makes the jump to people, but it doesn't really go very far because it's not very good at spreading from person to person. The R naught, the number that quantifies how contagious a disease is, the basic reproductive number, if this person has an R naught of 1, that means on average they're going to spread the pathogen to one other person. If this disease has an R naught of 2, then this person on average will spread it to 2 people. If the R naught is less than 1, there will be no epidemic or pandemic. The disease will essentially sputter out. This is so-called stuttering transmission. So this is this third stage where basically the disease doesn't really go anywhere. The fourth stage, and the one that we are experiencing with the COVID-19 pandemic, is when we have a pathogen that comes from an animal, it spills over into people, and then the pathogen mutates such that the R naught is greater than 1, meaning for every person who becomes infected, they're on average going to spread it to more than one person. A lot of work has been done in recent years to try to predict where and when and understand how these spillover events happen. And not surprisingly, these spillover events are pretty complex and are the result of interacting causes that have to do with ecological factors. So, are there different types of animals that can act as reservoirs for the pathogen? And are there people with various kind of susceptibility to their kind of transmission? Epidemiological or genetic factors. So different viruses, different bacteria have different traits that maybe make them more or less likely to spill over or make that jump from animals to people. And then the type of environmental changes that increase the interaction between people and potential animal reservoirs. So, land use change, for example. So, if we are building our houses or our cities further into forest areas, for example, we are increasing the probability that we're going to come in contact with a reservoir, an animal reservoir. So we can look at these different factors that influence how pathogens make this jump from animals to people. And this is from the reading, I think does a really good job of kind of summarizing how we use this kind of model to understand and hopefully predict pandemics. Because pandemics are not something we need to live with. If we can understand how this is happening, we can identify the mechanisms and identify the locations, hopefully, to try to stop it. But different human behaviors, environmental changes, and then aspects of the biology of the pathogens themselves dictate how likely this person is to be infected by a pathogen infected animal. And a lot of these things need to line up in order to have a spillover event. So I'm not going to go through all of these right now. The reading does a pretty good job of kind of explaining what this means. But essentially, if you've ever heard the saying, the stars need to align, the planets need to align, a lot of things have to go right for a spillover event to happen. And I say right in the not good sense, but in the sense that a spillover event needs to happen. So, what we care about as public health practitioners is what are the factors that influence this probability of infection from animals to people? So, we need to know something about basically if we're talking about an animal reservoir, like a group of primates, how prevalent is the infection in this animal reservoir? Is it a super rare disease and it's very, very unlikely that this animal has a virus? How likely is it that that duck you see has something that could make you sick? If we never come in contact with an animal reservoir, we won't get a disease from them. The more we come into contact with animal reservoirs, the higher the probability that we are going to be exposed to viruses. And then the third factor is how likely is it that if we do come into contact with a pathogen infected animal, how likely is it that we, as in humans, are going to become infected? And a few th- a number of things influence this kind of contact rate between animals and humans, and I'm going to talk about a couple. We mentioned climate change a little earlier, and some other factors that you've probably been seeing in the news a lot because of the COVID-19 pandemic, um, specifically wet markets and bushmeat hunting. So wet markets, if you're not familiar with the term, are essentially markets that sell a number of kind of goods, but what distinguishes them or what makes them high risk or public health threats potentially are the fact that they sell live animals. So I've used this time of self isolation, to become a master in graphic design. So this is something I'm very proud of. This is a skill I really managed to cultivate and developed, and I'd like to show you guys an example of some of my work that I'm particularly proud of. So up here we have a forest area, and over here we have another forest. Maybe these are in rural parts of Southeast Asia. And let's say that we have a market, a so-called wet market, that brings people together to sell food, spices, and live animals. And let's say that someone comes to the market and is bringing animals like this cute little guy who is highly trafficked. And let's say that these animals are taken from a rural forest area and transported to this central market. And let's say that another market vendor has taken some bats from this forest and transported them to the market. Now you have conditions in which people and these animals from different parts of the um, country are all mixing and coming together in close contact. Now we have conditions that increase our exposure to potentially these reservoirs of pathogens. And then let's say down here, we have a city, an urban center. That's this kind of blob down at the bottom. So people who go shopping in the market and maybe are exposed to a spillover event could take the virus back with them to their home city. And if that pathogen has acquired the ability to transmit from person to person, and this city happens to be, let's say, one of these mega cities where we have a lot of people living in close proximity to each other, we have the conditions for potentially a pandemic. Bushmeat hunting is another behavior in people that places us at increased contact with zoonotic diseases. This is a bushmeat hunter in West Africa. Bushmeat is essentially any animal that you can hunt for food in the forest, including primates. This is a bushmeat hunter who is taking a baboon primate back to his village. And you can see that there is quite a bit of blood and not a lot of protective kind of barrier between the person and the primate. So if this primate has a virus or a pathogen, and this bushmeat hunter maybe has some cuts or scrapes, there's a lot of mixing of blood that could allow the virus to spill over into the human. If that virus is capable of then spreading from person to person, and this bushmeat hunter takes that virus back with him to his community, we have the recipe for a potential disease outbreak. So Ebola naturally circulates in bat reservoirs. This is called the enzootic cycle. A number of different viruses circulate in bat populations, and this is always happening. Bats harbor viruses. Other animals harbor viruses too, but for Ebola, there are bats that are out in the forest and they have Ebola. This isn't generally an issue or a problem if humans don't come into contact with this enzootic transmission cycle. If through human behavior or changes to the environment, humans come into contact with this transmission cycle, for example, the virus can sometimes go from the bats to other animals, including primates, because primates are out in the forest sharing territory with the bat reservoirs. Uh, Primates can become infected as well. And if through human behaviors like bushmeat hunting, we are coming into contact with the primates, this is how spillover events can happen. And if we look at the largest Ebola outbreaks in history in West Africa and compare them on this side to deforestation rates marked by pink pixels, we can see that areas that are experiencing these Ebola outbreaks are also areas that are experiencing a lot of deforestation. And deforestation occurs because of things like logging and human settlements, this puts people into increased contact with these bat reservoirs. So here's a bat. And before we malign the bats too much, bats are very, very important to ecosystems, and human health and well being relies on bats a great deal. Bats are very important pollinators. But bats also harbor a lot of viruses that can be emerging infectious diseases in humans. And so, with a disease like Ebola, where the virus comes from bats, sometimes can spill over into other animals like non human primates, and that this is all occurring in forests, let's say in West Africa. This, and I told you guys I am becoming a master at graphic design. This is how Ebola outbreaks happen. Let's take an Ebola virus that is found in its natural reservoir, a bat. And let's say that this primate comes into contact with this bat and it becomes exposed to the virus, let's say through bat droppings. And now this primate has the virus. I showed you a picture of that bushmeat hunter where contact can occur between the hunter and the primate, and the virus can then get into the human. What increases the frequency of this kind of scenario? Well, things like logging roads. So if this natural cycle is occurring deep into the forest and there's no one around to be exposed to it, we don't have epidemics and we don't have pandemics. How do we get pandemics? Well, we need a person to get sick. And what allows people to get sick and to come into contact with this natural cycle? Well, things like logging roads. So if you look at this road, if this wasn't there, it would be a lot harder for these bushmeat hunters to get deeper into the forest. But now, because of deforestation and logging activities and so forth, this allows people to travel deeper into the forest and increase their contact with this transmission cycle. And this is the condition that I like to call the Goldilocks zone of deforestation. If we have a dense forest, this natural cycle is occurring. The virus is circulating around between bats, and sometimes it gets into other animals. But if there's no people around, that's not really a health issue. We can also get rid of disease risk entirely by clear cutting the rainforest, but that is not ideal because turns out we need trees. If we have an in between scenario, let's say the construction of these logging roads, we have a scenario in which we have enough trees for the virus and the bats and the primates to exist, and we have this mechanism for people to travel deeper into the forest. This is actually the highest risk for epidemics and pandemics. So I promised you guys more amazing graphic design. Here you go. Let's say these yellow triangles are little villages, let's say in West Africa, and that this green blob is a forest, and that these stars are areas in which humans are coming into contact with pathogen infected bats or primates. You can see that if the forest is mostly dense and untouched by activities like logging, that bushmeat hunters can really only go so far because the forest is pretty dense, and so there's limited opportunities for contact to occur. Now, if we were to build a logging road, here denoted by this red line, this bushmeat hunter can now travel deeper into the forest and increase the number of contact points with the Ebola virus. Oh, that's kind of cute. Turns out that bats are actually responsible for a lot of zoonotic viruses. A lot of emerging infectious diseases in humans come from bats. Ebola, SARS, Marburg, and more have been traced to the bat, the only mammal capable of sustained flight. Wouldn't you know? But why? Why do bats have so many viruses? Good question. So it turns out bats are pretty unique. Bats have very high functioning immune systems. And it turns out that viruses in bats can actually replicate, and the number of viruses within a bat can grow faster in a bat without actually hurting or making the bat sick. And because the bat is able to resist the viruses, when that virus does make the jump into, like, let's say a primate or a person that doesn't have a good immune system like a bat's immune system, that virus becomes extremely virulent and can wreak a lot of havoc and cause a lot of damage. So bats can cover pretty wide geographic areas, and they can contain a lot of pathogens. And it turns out when a bat is flying around, their body temperature gets really high. Their body temperature peaks, and this resembles like a fever in people. Like when you get a fever, your body temperature spikes. So the pathogens that are found within bats have actually evolved to withstand these temperature spikes. So when the virus ends up getting into a person, that virus is already used to a creature that has high body temperature peaks. So when a human's defense mechanism, which is, getting a fever, the reason we get fevers when we're sick is that's a natural defense to try to kill the pathogen or destroy the pathogen. But these pathogens that come from bats are already used to a creature that has spikes in body temperature. So that when a human's uh, fever or body temperature is increased, it doesn't bother the pathogen as much. Bats can also get stressed out due to things like deforestation and habitat loss. So, if a bat is naturally circulating a virus in a dense part of the rainforest, if human settlements start encroaching or deforestation rates start increasing, Uh, this will actually stress the bat out. So if a bat starts hearing a chainsaw, it's going to start getting stressed. And when a bat gets stressed, this allows for infections to leave the bat because a stressed out bat tends to excrete more viruses. Just like when people get stressed out, if we have the virus that causes cold sores, we tend to get cold sores. That's the virus being expressed. This same kind of thing can happen in bats too. But when a bat gets stressed, potentially that means more disease, more virus like Ebola being excreted. What's another way of stressing out a bat? Well, let's say you bring a bat from its home habitat in the jungle to a wet market. Do you think that's going to stress the bat out? Probably. And if you're bringing a stressed out bat that has viruses into a space like this, now all of a sudden you have a lot of potential for a spillover event to happen. And it's because of things like this that lead disease ecologists, public health epidemiologists, and environmental health scientists uh, to really like not be surprised with the fact that we have zoonotic pandemics. This is from a prominent disease ecologist, Thomas Gillespie. He said, quote, "I'm not at all surprised about the coronavirus outbreak. The majority of pathogens are still to be discovered. We are at the very tip of the iceberg." So, an emerging field of public health and environmental health is trying to understand these zoonotic spillover mechanisms so that we can identify high risk areas and hopefully stop the next COVID 19 pandemic. Because these mechanisms exist, these spillover events have been happening and most likely will continue to happen as we put more and more pressure on the environment. And as things like climate change and deforestation and other risk factors for zoonotic spillover increase. The other coronaviruses, so we're all familiar now with COVID 19, but MERS and SARS are other coronaviruses that have impacted human populations in recent years, have zoonotic origins as well. So MERS is thought to come from camel populations and made the jump from camels to people. This is a zoonotic spillover event. And SARS is thought to come from bats and civet cats, strangely enough. So if you find this topic interesting, if you want to know more about zoonotic spillovers, if you are frustrated with the COVID 19 pandemic and want to do something about it or maybe better understand these mechanisms, I would highly recommend the book Spillover. You can get it on Amazon used for pretty cheap. It is a great read. It goes all into the stories of these zoonotic spillovers and really gives a good, clear depiction of kind of the social and ecological factors that contribute to zoonotic spillover. It's a great read. It's on my bookshelf. And if you're looking for some self isolation reading and looking to better understand why diseases like COVID 19 happen, I would highly recommend the book Spillover. So, this has been Dr. Bales' book club. I hope you all stay well. I hope you continue to read more about zoonotic spillovers. It is a uh, fascinating process. It is a complicated process. It is the reason why we have COVID 19. Um, and if you are feeling frustrated with the current state of affairs in the world, um, why not be part of the next generation of public health fighters that does something about this? Uh, I want to issue the challenge that we can learn about these mechanisms and ultimately we can prevent the next pandemic from happening. So stay well, wash your hands because viruses don't like soap, and I'll see you next time.